In this video, we talk about CPU power consumption and its trend over the years. We make some comments related to the clock rate and performances, but mostly we analyze the power consumption formula and what it tells us. In order to calculate the power consumption of a CPU, we recall that in the electric dimension, power is voltage times current, or more generally, the quantity of energy consumed in the time unit. The first thing we have to do is understand what kind of a load we have in the CPU, or in other words, in which way CPU consumes energy. We need to know if we have a resistive, inductive, or capacitive load. But this is easy because the only thing we have in the CPU is a particular kind of transistors called MOSFET. So, as you'll see in a moment, we have a capacitive load. This is, for example, the CMOS configuration used in integrated circuits. Through the MOSFET transistor, we build the logic gate used to build every other components like a decoder or an adder. But at the end, we have to imagine the CPU as a piece of silicon full of transistors, so like a sea of MOSFETs connected to each other. So let's see how the MOSFET works at a very basic level. Starting from the basics, the MOSFET is nothing more than a very fast switch. We use two types of transistor, N-type and P-type. For our purposes, we just think of the transistor as a switch. The N-type transistor is on, closed circuit, if I apply a 1 or higher voltage to the gate, and it is off, open circuit, if I apply 0 or lower voltage to the gate. The P-type works the opposite. It is off if I apply 1 and it is on if I apply 0, summarizing our transistor as switches that we can very fast turn on and off and that are very small. So basically what happens inside the CPU is that continuously some voltages are applied on the gate of some transistors, and this makes a current or an electric charge flowing through the transistors to lead some other transistors. But when you put a voltage on the gate of a transistor, you basically are putting some charge in the capacitor you see through the gate of the MOSFET. So, basically, in the CPU, we have mostly capacitive load. It can be proved that the energy we need to charge a capacitor is 1/2 CV square, where C is the capacitance and V is the voltage applied to the capacitor. This energy is consumed in the transition operation when the transistor switches from 0 to 1 and vice versa, so in every charging or discharging of the capacitance. If we imagine to charge and discharge continuously the capacitor, the power is proportional to the switched frequency or the number of times we switch the transistor on and off. Of course, in a CPU, the switched frequency is a function of the clock rate, so the power consumption is proportional to the clock rate. So here the power consumption equation of a CPU. This equation can explain us a lot of things. The power is proportional to the equivalent load capacitance, to the square of the voltage and to the clock rate. If you want to lower the power consumption, which is an item more important because of mobile phone and battery powered devices, you have to lower capacitance or clock rate, but especially voltage because of the square relation. Let's see every factor one by one. We start with our little but decisive capacitance. We have to imagine the CPU as a grid of metal lines which lead thousands of capacitive loads. This capacitance comes from the MOSFET gates, but also from any parasitic capacitance in the circuit. We have a lot of them because every time we have a different voltage level between 2 points, we have a capacitance effect between these 2 points. Calculating the equivalent capacitance is not easy, but it can be done with the help of simulators. Anyway, the designer has to keep low this equivalent total capacitance, especially the parasitic ones, which is responsible of power dissipation, even when the MOSFET is not working, so when it is not switching. In order to keep low the power consumption, we could lower the clock rate, but this would affect the CPU performance too. Remembering the performance equation of a CPU in my previous video, we have this other equation. Lowering the clock rate makes lowering the power consumption, but it makes increasing the CPU time of execution, so it causes the lowering of the CPU performance. So chip factories have to find a trade-off in order to keep low the power consumption without to affect badly the CPU performance. We'll see how this can be done in a moment. Best thing to do in order to lower the CPU power consumption is lower the voltage. And through the years, this has been done many times. We went from 5 volts to 1 volt in some decades, but this has been possible because it was possible to miniaturize the transistor more and more. Remember the gate length measured in nanometer? It gives the size of the transistors. Factories are working now at 5 nanometer, but some physics problems in the technical operation have to be passed for further miniaturization. Now let's see the CPU trend over the years in relation to clock rate, power consumption and miniaturization. I'm sorry this diagram is the best I found on the web, it is quite old, it reports till 2010, but is still useful to understand the long run. The green line is the number of transistors inside the CPU, and you can see till 2010 it has increased a lot, and this means miniaturization. Intel always lowered the gate length until 2010 at a fast pace, but now the pace is slowing, and the 7 nanometers is planned for the 2023. The blue line is the clock rate, and you see from the 70 to 2005 clock rate has improved of a factor of 5000, but after 2005 clock rate has not increased anymore. The light blue line is the power consumption, and you see it has increased of a factor of 100. That because we lowered the voltage from 5 volts to 1 volt, and this lowered the increase of the power consumption caused by the clock rate improvement. Of course, in order to lower the voltage, we had to build the transistor smaller and smaller. But after 2010, what happens? As I said, miniaturizing is always more difficult, so further lowering of the voltage is difficult. Clock rate is still not increasing in these years, and we are around 5 GHz. All the improvements in these last decades have come from the parallelization. If we cannot improve the clock rate because of power consumption, we improve the throughput, so we improve the job done in the time unit, doing things in parallel. In this way, we increase the data processed without increase the clock rate. For this reason, the multi-core CPU came in these last decades, where each core is like a little CPU. So that's where multi-core architecture comes from the struggling battle between power consumption and performance. The problem of the multi-core is the software, because in order to exploit the parallelization, we have to adapt the software, otherwise you still ask all the tasks to one core only. The software has to divide the tasks to several cores in order to improve the throughput and get an advantage. Please leave me a comment and let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.